A very good afternoon to all of you. I am your teaching assistant Mujibur Rahman for the course Advanced Soil Mechanics, which is being taught by Professor Shrideep Shekhar. So in this session 7, we are going to discuss about the contents that has been discussed with you in the lectures or the content that have been shared in the NPTEL portal. So in this session, we are going to conclude the module 3, which is about the shear strength of soils, and we are going to study or we are going to introduce the new topic of stress path. So in the last session, which was the session 6, we have observed or we have seen the different testings that we can perform in the track shell, which includes the unconsolidated undrained test, consolidated drain test, and consolidated undrained test. And we observe what difference lies, what are the main difference that lies in all the three tests, and how the stress strain response varies in the three tests. Now, briefly concluding that part about the comparison of the stress strain curves for the UU, CU, and CD, we can see that the stress strain response all the three, it's altogether not the same, but they are similar, where the stress strain dielectric stress reaches a peak and then it drops while we are sharing the sample, and this variation is with the volumetric strain. And if we talk about the UU and CU test, if we observe the variation of the excess pore water pressure with the volumetric strain, there is the initial pore water pressure in the UU test, and then which increases because we are not allowing the dissipation. But as you saw in the test, that UU calculations are not important in the excess pore water pressure calculations are not important in the UU test, because it results in a single effective stress Mohr circle, which is not giving a information about the effective stress failure envelope or effective, since we have the total stress envelope, failure envelope, and we don't have an effective stress failure envelope for in the UU case. But if we talk about the CU, consolidated undrained test, while in which the what we are doing after the consolidation, the pore water pressure is allowed to develop in the sample by not allowing the pore water pressure to dissipate, or we can say that we don't allow any further dissipation of pore water pressure during the shearing stage. As a result, there will be the build-up of pore water pressure during shearing, and this UBP is actually the after consolidation. This either the pore water pressure may be equivalent to 0, or it may be equivalent to the UBP, correct? And then it increases since it's a CU test. However, in case of consolidated drain test, we don't have a concept of excess pore water pressure in the CD test. What we are more interested is to see the volume change. That's what we have seen. There is a change in the volume with the volumetric strain. There is a continuous increase in the volumetric strain, and it depends upon the behavior of soil that we can take. And in this, the volumetric strain is volume change is occurring, and it is increasing during the shearing process. And vis-a-vis, you can see there is a increase in the dielectric stress till it reaches the peak value, then it starts to decrease. Now, this is like a general overview of the comparison of stress strain behavior for the UU, CU, and CD test. Now, as you see, you can see the stress strain response for you have seen this stress strain response in which the soil first in the dielectric stress increases at small strains, then reaches a peak, and then have a softening till it reaches a critical state value. Now, what we have the different shear strength parameters. Like I would say, like if we want to select a criteria to say where this soil will fail, what criterion should we consider based on this stress strain variation? So for that, we need to understand a few things, few aspects of it. We can decide the criteria based on the 5 things. Either it can be the peak dielectric stress, which is at 1, or maximum principal stress, this one, limiting strain, which is at 0.3, critical state, which is at 0.4, and the residual state, which is at 0.5. Now, if we talk about the peak dielectric stress, which is 0.1, this generally we are using for the dilating soils. Since we will get this kind of response for a dilating soil where we have a dominant peak there, so we can use this peak dielectric stress as a criteria for determining shear strength in case of dilating soils. And one more thing we should understand that this shear strength is not a fundamental characteristic of soil, and it changed with the stress state of the soil, correct, and also with the confining stress. So this one if we talk about the peak duetic stress, this can be one of the criteria for the dilating soils. Similarly, maximum principal stress, here we have the maximum principal stress ratio. Fine. Maximum principal stress ratio, this we can use as a criteria. It's mostly we are using it for the undrained cases, this maximum principal stress ratio, and this is generally like this maximum principal stress ratio is generally used when the stress strain response doesn't have a prominent peak in the stress strain response. Similarly, this limiting strain, it's generally like if some soils are there in which large strain is needed to mobilize the failure conditions such as the NC clays. So we want to restrict the strain at some limit, and for that soils we are using this limiting strain as a criteria. Now this critical state, generally like for OC over consolidated soils, there is a drop in the stress, correct, after the peak value. You can see there is a drop in the stress after the peak value. So for NC soils, the stress strain reaches the critical state directly, and 0.4, this is actually the critical state, and at critical state shearing takes place at a constant volume. Like if we talk about this 0.4, at this stage shearing, what is a critical state? It's a kind of a definition for a critical state, that the critical state is defined like as a state at which the shearing takes place at the constant volume. And for the OC soils, we can take this as a criterion for determining the shear strength. And one more thing, like this critical state is actually the fundamental property of soil, because irrespective of the initial state, whether it is a loose or dense or whatever be the conditions, the soil is going to reach this critical state. And for cohesive soils, in case the soil is sheared beyond the critical state, we can consider this 5, which is the residual state, as a criteria for determining the shear strength. Fine. So at this state, while at this residual state, there are the formation of narrow shear zones due to the reorientation of clay particles. Fine. And this condition generally develops when large strain has occurred, as in case of landslides or like slow failures, this residual state. So in that cases, like landslides or slow failures, we can consider this residual state or 0.5 on the stress strain response as a criterion for determining the shear strength. Correct. After that, we have went through the different factors affecting the shear strength. Now it has been grouped into two categories. One is the natural factor and another induced factor. Natural factors include the mineralogy of the grains, particle size distribution. Mineralogy, or what is the built up of the grain, particle size distribution, PSD. Like if it is a well graded, if it is a well graded, the strength of the soil will be different. If it is a poorly graded or gap graded, then the strength offered by the soil is different, and it's affected by the shape of the particles. Like rounded will have a different strength as compared to the angular or semi-angular. Similarly, the arrangement or the way how we are packing the soil, that's also going to affect the strength of the soil. Water content and void ratio, which are considered the initial state of the soil, they are also going to affect the strength of the soil. Now after that, we have the stress history. Stress history means what is the stress that the soil has experienced in the past, whether the present stress are equal to the stress which maximum stress that it has that has been experienced on it in the past, then this is going to affect the strength of the soil also, and the in situ stresses. Fine. So these are the natural factors which are affecting the which are going to affect the shear strength of the soil. Fine. And in the induced factors, we can say like these things we don't have a control, correct. And in this induced factors, we can take care of these factors while dealing with the soil. Like it all depends upon the sampling, like the stress change that occurs during the sampling, or the initial state or the initial state impulse before loading or testing. Initial state impulse before testing, like before we are going to test the sample in the triaxial, what are the initial state we are chosen, and the before loading, what are the stresses applied to the loading, like whether it is the isotropic consolidation or anisotropic consolidation. Method of the test, which test we are going to do. Then the drainage condition, whether we are allowing the drainage or not, it has an effect on the shear strength, as you are seeing in the previous module. Then the rate of loading, this will affect the whether the it will affect the strength, and also it will affect the rate of development of forward pressure. So these two are interconnected or interrelated. And also the criterion which are being adopted to define the shear strength. As in the last slide we say that based on the different like the type of the soil, we can have a different criterions or what actually is the need of the need in the field. Now some limitations of the triaxial test, like in the session 3 or session 4 we started that triaxial is like a it has some advantage over the directional test, but now this triaxial also conventional triaxial also have some limitations. So the sigma 2 not considered, it means that the intermediate stress, since we know that there are three principal stresses, sigma 1, sigma 2 and sigma 3, and in the triaxial we are assuming sigma 2 is called sigma 3, but in the actual case the sigma 2 is not equal to sigma 3 in the field. So this intermediate stress is not considered in the conventional triaxial test. And also rotational stress not considered. Rotational stresses means if we talk about if we have this test sample, the sigma 1 and sigma 3 are always acting like this, correct? Fine. So but in some cases, like we have the earthquake case or cyclic loading, where there is a continuous change of this I mean to say these stresses. For example, in this one, like here sigma 1 will be maximum, here sigma 3 is maximum. So like I mean to say that in triaxial there is rotational stress are not considered in the as I told you in the cyclic loading or earthquake conditions, there is a continuous rotation of the stresses. But in the triaxial, the sigma 1 vertical stress will be always a principal maximum principal stress, and sigma 3 will be always a minimum principal stress. But in actual cases, in the field, there is a rotation of stresses that it doesn't consider, or even during slow failure there may be the rotation of stresses which this triaxial doesn't consider. After that, we have seen that in the last module, plane strain condition, which is actually the more convenient to use in the field. It replicates the more field conditions, but that plane strain condition cannot be considered. But yes, to be some experiments or some devices have been developed which actually takes into care this plane strain condition in the laboratories also. After that, it's not necessary that always in the field we have isotropic condition. In the field there can be the anisotropy also. That's the difference between the vertical and horizontal stresses. But to do that, it's little difficult in the conventional triaxial. We can do it, but it's difficult. Generally, we prefer the isotropic conditions, which actually may not simulate the actual field condition. Effect of end constraints. Like in the first lecture, also about the shear strength of shear, when we talked about the conventional triaxial, we told there is upper loading plate and lower loading plate. They are actually loading. When we are loading the sample, it's not necessary that the loading will be uniform. So that's what they are also the ends are the end restraints are there, which are also affecting the results. So they are also is one of the limitations of the triaxial test. And also the last one is the strength that is obtained from the conventional triaxial test. They are actually higher, or it's higher than the field strength. Fine. So these are the some limitations. And the sigma 2 not considered, there are some triaxials which have been developed now, which we call the true triaxial, where we can have control over the sigma 1, sigma 2 and sigma 3. All the three stresses can be captured individually. So that's advanced that we call the true triaxial, where we have control over the sigma 1, sigma 2 and sigma 3. All the three stresses can be changed simultaneously during the testing. Now this was all about the module 2, where we talked about the shear strength aspects of the soil, whether it was cohesionless soil or a cohesive soil. Now in the module 3, we have a new topic that we are going to discuss briefly, is a stress path and its representation. What stress path is and how we are representing this stress path. Now in the module 2, you have seen that when we are loading the sample, the stress strain response is like this. Fine. Or it can be this if it's NC. Fine. But that, if we talk about either the stress strain response is this or it can be this, fine. This plot is not telling us anything about the way the soil has failed. it's just a response, or how it has from initial state to final state, how it has reached the failure state. This is the one uh, situation where we need the knowledge of the stress path. Or in the field, for example, if in the field where we have initially there was a ground there, fine, then we did some excavation. So for replicating this condition in the experiments, we need the knowledge of stress path, because initially there is no, like, there will be sigma v and sigma h acting on the soil sample, but once we do the excavation, the soil sample, for example here, its sigma v is getting reduced, correct? So in order to see the behavior of the soil when we do this excavation, we have to follow a particular stress path. So this is the second scenario where we need the knowledge of stress paths to determine the behavior of the soil, how it has reached the failure, and to replicate any field condition in the laboratories, we need a knowledge of the stress paths. So what a stress path is actually? So it's actually the 2D graphical plot representing theoretically or experimental relation between the two stress parameters. Fine, it's actually a 2D plot which actually it relates the two stress parameters. What are those two parameters? Either it can be the axial stress or radial stress, or it can be the P and Q, or it can be the T. Or we have seen this parameters in the last lecture. So why this is important? It's a convenient way to visualize how the stresses change during loading or unloading, and how it approaches the failure state. As I told you, that this stress path will tell us how the state of the soil changed from the initial state to the final state, or how it has achieved the failure, how it has approached the failure. It's important to simulate stress sequence in the lab which is relevant to the field condition. Again, the same thing, that if we want to study any field scenario, then we need to understand the knowledge of this stress path, how the stresses are changing in the soil, so that we can replicate the same in the labs, and we will get a better response of that. Stress path is a function of soil type, stress history, drainage conditions, and the loading sequence. Yes, it's true. It depends on the soil, the type of the soil, what is the stress history, drainage conditions, and the loading sequence that we have applied during the testing or in the field. What is the loading sequence? Now, this is just a quick review. Stress path is a representation. We have done it in the last, I think, in the last session. We are representing the stress path either in terms of axial or radial, in terms of sigma A and sigma r, axial and radial stresses, and the failure slope is given by failure line, which has slope of kr, or we can represent in terms of q and p, where p dash is equal to sigma axial plus 2s sigma radial divided by 3, which can be given in terms of principal stresses sigma 1 dash plus 2s sigma 3 dash divided by 3, and q is equivalent to sigma axial minus radial, which is equivalent to sigma 1 minus sigma 3 dash, sigma 1 dash minus sigma 3 dash. Or we can give in terms of T and S dash plot, fine, where S dash is the average of the sigma A plus sigma R, and T is the difference sigma A dash minus sigma R dash divided by 2, fine. Now comes the implementation part, where we are actually plotting the stress paths. This is just like to understand how we are using the knowledge of stress paths for understanding the loading sequence, fine. So we are going to plot the stress paths for these stress states. I will do one or two, rest you can try, or I will try to complete them as soon like quickly, because there are a lot of things to discuss. The first is the isotropic increase in the vertical stresses. It's in the classes we have done it. Just a brief, quickly I will go through it. For example, I will plot it on the sigma A sigma R axis. This is sigma R dash and this is sigma A dash. Fine. It's like quickly we can do it on sigma and sigma R. If we talk about the P and Q or R, T and S, then we have to do some formulations. So for example, the initial state, it's here, like this is a isotropic line, fine. So isotropic increase in effective stresses, there is an increase in the effective stress. Isotropic increase, which means that there is a around increase. If there is a around increase in the stress, it means that delta sigma A will be equal to delta sigma r dash. Correct? So we will represent this, since they both are equal, it will fall somewhere on this line. Let us keep it as a dash. Fine. So this point will represent this condition, sigma delta sigma a dash equal to delta sigma r dash. Isotopic increase in the effective stresses. Fine. Now B part is increase in axial strain or axial stress, increase in the axial stress and constant sigma r. It means that if sigma a is the initial, if sigma a is the initial stress, axial stress, it has been increased. Let's assume by delta sigma a. Correct? And constant sigma r. So sigma r is constant, it means the change in delta sigma r is 0. Fine. So where will this point lie? So sigma r, change in sigma r is 0. Correct? So only sigma a is increasing. So sigma a is increasing, it means that it will go up like this. Fine. Let's call it B. Fine. Correct? Now sigma r increases. This we can name it as OA dash. Correct? And this one we can name it as increasing sigma a, and constant we call it A dash B dash. Fine. Correct? Now, yeah, because the naming is here given A dash B dash. Now we have delta r increases. C is sigma r increases, sigma is constant. So change in sigma a dash is 0. Correct? Fine. Now as of now, and we are increasing this, we are increasing the delta sigma r. Fine, we are increasing. So since it's an undrained condition, so whatever be the increase in the delta sigma r, it will reflect in the delta sigma a also. Fine. So how will it go? This one. So this will be it's a undrained loading. So for this case, we have the stress for B dash C. So delta sigma d is 0 and delta sigma r increases. So it will go to B dash C here. Correct? Delta sigma dash change is 0, but due to increase in the delta sigma, there will be the generation of forward total delta U, which will be like kind of like it will add here also and it will add to here also, but externally we are not increasing the delta sigma a. Correct? Or we can say for like convenience, delta sigma a is equal to delta U for undrained case. So it means that this is delta U, this is delta U, and delta U is equal to delta sigma r. Correct? Now the last case that I want to discuss with you is the part D, where there is an increase in delta sigma r and there is a constant sigma dash axial strain, and it's a drained case. And since it is a drained case, there will be no like generation of this delta U will be 0. So in this case we have to represent by B dash C dash. So in this case delta U will be 0. So change in sigma a dash will be 0 and change in sigma r will be delta U. So we can simply draw a line from here to here. Let's do another color. Call it C dash. So C dash actually represents the B dash. C dash is the stress for the D point, where sigma there is an increase in sigma r and there is no change in the axial stresses. Correct? So this is the one of the ways of representing the different stress states that we can achieve. And this I have plotted in the sigma and sigma r, which is easy to do, or like easy to perform, because whatever will be the increase we can increase in sigma, or whatever the increase or decrease in sigma r we can do. In case you want to plot it in the MIT plot or the Cambridge plot, we have to do the calculations for P and Q. Now after this, if we talk about the stress plots, for example, this stress state is there, sigma, like for example, we have this stress state P and Q, fine, and this, there are the states A dash, B dash, C dash. For example, there is another state here going here, something E dash, F dash. Like this will not, if we look at this plot, this is giving information about the how we are loading the sample. This is not talking of this is not telling us anything about the bounce or a failure about the soil. Up to what we have to load the sample, or what are the bounds in the extension or the compression side. That will give us the idea that if we are going to load a sample of a soil, we have to load it up to a certain limit. After that, this state will not exist, it will fail. So there is a need to actually to include a failure lines or a bound to the stress path. Then the stress paths become more meaningful to us. So that's why we need a failure line. So locus of stress points is not relevant unless the binds are defined. So it means that there is a need to have a failure line. The reason for it, if we don't have this failure line in the stress in the PQ plot, then we don't have an idea that which state of the soil is not going to exist, or which will, or how it has, which is the failure state of the soil, or what are the stress states which a soil can hold without failing. Fine. So in all the three representation, whether it is sigma or A or sigma R, or the TNS or PNQ, we have determined these bounds. And for the compression, this is the bound in the stress in the axial and radial stress plot. Similarly, this is the extension. The slopes are tan square 45 plus 5 by 2 and cot square 45 plus 5 by 2. In the TNS plot, this is the isotropic line, because in this line the T will be 0 and this will correspond to the isotropic state. And the inclination of those failure line in the compression and tension is sin phi dash and minus sin phi dash respectively. And in the QP plot, in this line P dash, PP dash, or the horizontal line, you can see there is no shear stress acting on it. So this is the isotropic line, and the failure bounds in the compression is KFC, given by the slope of which is 6 sin phi dash divided by 3 minus sin phi dash. And in the extension, we have slope of minus 6 sin phi dash divided by 3 plus sin phi dash. This is from extension side. Now, if we talk about the some like stress path for the isotropic consolidation. So why actually if we have a soil, if we bring the soil from the field and we can directly share it, what is the need to consolidate the soil? So if we talk about the different stages of the triaxial, we are first doing the saturation stage, correct? We are saturating the sample, we have the saturation stage, and then we have the consolidation. Then we are sharing. The thing is, what is the need to do these two stages? Why we need to perform these two stages? Actually, the thing is, the main purpose of doing this duty or doing this job is to replicate the field condition. When we are saturating the sample, we are ensuring that all the voids are filled with water. We are pressure saturating the soil, and once it is consolidated, we are doing consolidation at a confining stress which belongs to the field. And once the sample is getting consolidated, so whatever the consolidation soil is achieved in the field, we are assuming that same consolidation levels, same dissipation, same amount of pore water which has been dissipated from the soil, and at this confining stress, how much the consolidation should happen in the soil, that we are replicating in the field. After that, when we are sharing the sample, this we can consider as similar as a field sample. Not as, we can't say it is like exact sample, but the results will be similar to that, despite the fact that the strength will be higher. but it will give us an idea that how the soil will behave in the field. So these two states are mainly to replicate the field condition, and we are doing this consolidation stage to replicate the field. So that's why this consolidation is done to simulate the recovered stress history and stress state before sharing. What does stress history mean? In case stress state and stress state, it means that in case we are going for the anisotropic consolidation, where there are the vertical and horizontal stresses are not same. In that case, we can perform the anisotropic consolidation and let the soil consolidate, and then we can perform the sharing. So this consolidation is for actually bringing the soil sample to replicate the field conditions. Fine. Now, once we have this is the initial isotropic consolidation stage where sigma 3 is applying, and then we have done some increments in it, delta sigma dash, sigma 3 plus delta sigma, and sigma 3 plus delta sigma. Now, since it's a sigma A and sigma R plot, correct, and this is the isotropic line, this dashed line is the isotropic line, fine, and along this line the stresses will be same, sigma n and sigma R will be same. So this point sigma 3, this state A dash will lie on this point, fine. Now once we are incrementing it by delta sigma, what will happen? So at initial time, at t is equal to 0, delta sigma will be delta u. If you remember this formula, delta u is equivalent to b times delta sigma 3 plus a times delta sigma 3 plus delta sigma 1, correct, plus delta sigma 1. So b is equal to 1, so and a is 1 by 3, correct, or sigma this change in the sigma 1 is 0. So here you will get delta u is equal to delta sigma 3. So whatever the change in the delta sigma 3, that will come in the delta delta u, fine. So once so whatever be the change in the delta sigma, that will come in the delta q. It means that the effective stress will be 0, correct. So from a dash represents this initial isotropic consolidation point or phase, then and then this isotropic at t is equal to 0, delta sigma is equal to delta u, fine. So same increment will be there from a to b, correct. From a to b we will have a same this is the, or we can say a to b represents the total stress path for this stress increment from a dash to this let's call it b. And for b dash, since there is no effective stress is 0, so this effective stress point or effective stress path is not going to change. After that, if once this pore water pressure will start to dissipate, what will happen that the change in the delta sigma, whatever be the change we have applied, it will reflect in the delta sigma. So you can see that at this point cc dash will represent the this increment t, this at t is equal to t, delta sigma is equal to delta sigma dash, and after it's a kind of after some equilibrating time there will be dissipation of this pressure, and this delta sigma will be equal to delta sigma dash, and this will be represented by cc dash, and this increment here and here it will be equivalent to delta sigma is equal to delta u. Since the bounds are there, you can see that whatever the stress state we are representing, whether it is a dash, b or cc dash, it's lying between this kfc, which is the failure or a bound in the compression, and kfe is a bound in the compression. So whatever the stress states we have achieved in the consolidation, they are lying on this isotropic line. So it means that this isotropic state where there are equal around stresses, they are not going to share the sample. They are not going to deform the sample. They will do the, or we can say they will undergo the, it will cause the volumetric deformation in the sample, not the shear deformations, correct, fine. So cc dash is the final state where delta sigma is equal to delta sigma dash and delta u is equal to 0, and this is stress for the isotropic consolidation in the sigma a and sigma r plot. Now if we talk about the same thing in the t and s dash plot, so first is a dash, we have to determine the s dash, and we are done with that, this is the initial state, and when we do this at t is equal to 0, delta sigma is equal to delta sigma u. So our a will shift to b, and this delta sigma is equal to delta u, or you can say a total stress path will shift from a to b. Fine. And if we talk about the effective stress path, and delta sigma dash is equal to 0, so thus this b dash is not going to move, because why this is 0, because at t is equal to 0, whatever be the increase in sigma, it will be reflected in the u also. At some time, once this there is a dissipation of this pore water pressure, then delta sigma will be equivalent to delta sigma dash. So this delta sigma dash from a to b, while it has at this state b, this state b will correspond to the cc dash also, which means that that after the consolidation is done, there is no pore water pressure, so this state represents the final state of the soil after the consolidation. And in the PQ plot, and also you can see that this state, consolidation state, or which is the isotropic consolidation, it lies along this isotropic line, and which is well within this bounds. So these are not going to deform the sample or kind of shear the sample. Similarly for PQ plot, this plot is here. You can see this state is on the lies well within the bounds, and these are not going to deform the sample. So these are the three representations for the stress path for isotropic consolidation. Fine. So we can say this final stage is actually A and C. This final stage is actually A and C, but just for understanding part, this B has been introduced in it. Fine. Now after that, we'll see the consolidation, the stress path for the 1D consolidation. Generally, this 1D consolidation, when we talk about the 1D consolidation in the experiments or in the fields, the strains in the lateral directions are restrained, or like the in the experiments we have that shear rings which will prevent the lateral strains, and in the field we have the large area or large length by the strains in that direction or in the lateral directions are considered assumed to be 0. So we can use the earth pressure as rest K naught for the for relating the horizontal and vertical stresses, which is given by K naught is equal to sigma r divided by sigma A. Sigma it will be always in the effective stresses, sigma r dash divided by sigma A dash. Now for this NC soils, generally this K naught is given by Jacob's formula y minus 1 minus sin phi dash. For example, that we have a sample and A dash represents the initial part of the consolidation when we are applying the sigma 3 like this. Fine. So after t is equal to 0, when we have incremented it, when we apply the delta sigma 3 which is equivalent to, at t is equal to 0, it will be equivalent to delta u. Now if we calculate t is equal to delta sigma a plus delta sigma r divided by 2, sorry, it's minus delta, if we calculate delta t, it is delta sigma a minus delta sigma r divided by 2, and delta x is equal to delta sigma r plus delta sigma a by 2, and then determine the slope for it. We will come to know that this slope is equivalent to 1. So you can see that this K and C is actually the bound for the stress for the 1D consolidation. So it's this is for the isotropic line will be here, and this is the bound for the 1D consolidation corresponding to K naught. Fine. And at t is equal to 0, delta sigma is equal to delta b, delta sigma is equal to delta u, represented by point B in the stress path, but this line will be parallel to the isotropic line. As I told you, like if we determine this T and S or sigma A by simply, or no, it's not a T and S plot, it's a sigma A by sigma R plot. So sigma R by sigma A by sigma R will be 1. Whatever the increment will be there, this delta will be same in this and this. So the slope of this line will be 1. Fine. So it will be from B from it will be like from B to B dash. Sorry. So it will be from, just a second, yeah, so it will go from A to B, and again delta sigma dash is equal to 0. Delta sigma dash is equal to 0 because the stress is sigma, and like the total stress and the pore water pressure are equal, so the effective stress are 0, so B dash will be same at initial point. Now at time t is equal to t, when this like this pore water pressure will dissipate, what will happen, that delta sigma will be equal to delta sigma dash, fine, represented by point C, and this C will lie on the same K and C line, fine. So K and C line, which is actually the similar to like what are the stress state will change for the 1D consortium, they will lie on this line. This is actually the relation, how the stresses, vertical and horizontal stress are related for the 1D consolidation. So delta sigma, delta U will be 0, it will be represented by C dash here. So it means that at t is equal to 0, total stress path is given by A and A to B, fine, and at t is equal to T, where the stresses are pore water pressure dissipated, effective stress path is given by B dash C, this one, correct. So this is stress path for only consolidation in the sigma A sigma A plot. Now if we zoom this area, this portion, now you can see that this line represents the stress rate corresponding sigma dash, sigma delta is equal to sigma U. So this and this will be same, delta sigma U is equal to delta sigma, and similarly for similar increment will be in the delta sigma A because the isotropic consolidation, fine. So with this we'll be able, with the slope of this line K and C, which is 1 divided by 1 minus sin phi, we'll be able to determine this portion, fine, the increment, or we can say that B dash C, C dash. So delta sigma is equal to K naught and C sigma delta sigma A dash. Delta sigma A dash is equal to delta sigma. Now similar to the loading, how this unloading stress, how the unloading stress path will look like. Like for example, we have reached up to C dash when we are loading it. Now what if when we unload it? When we start to unload it, what is happening that it will not trace the K and C line back. It will have a different C, this unloading path represented by C dash D dash, fine, and it includes the, and like it induces the OC state, as you might have seen in the when we have defined the normal consolidation, E versus P, like this, fine. So when the soil was started to unload from this point, fine, so this becomes the pre-consolidation stress called yield stress. So whatever the stress now the soil feel here, it will be less than what it has experienced at the past. And also, why will not it drag back the K and C line? It is for a reason that when we are loading the sample or unloading the sample, there will be some amount of the strain, elastic strain, which will be developed in the soil, and this portion we call is the OC state, which will have high stuff. It will behave as an elastic part, fine. So it induces the OC state, and the unloading, when we are unloading the sample, how much we have to unload it, we have a bound. The bound is defined by the KFE. Unloading is restricted by the KFE, fine. Now for the OC soils, this K naught is given by K naught NC OCR 4 is for M, where M is equal to sin phi or M is equal to 1.25 sin phi. So this M is equal to 1.25 sin of phi. Now isotropic behavior is assumed during unloading for 1D, and the lateral strain is 0 because the state is OC state, because in the OC state the particles, the soil will be stiff, and the behavior and the deformation will have, it will be a elastic deformation. Now in order to relate the slope of the line, this line, unloading line, we are assuming the lateral strain is 0, and we have the equation delta sigma from in the modules, I think in module 2nd we have determined this equations. The radial strain, change in the radial strain, this will be delta sigma r dash by E dash minus mu dash by E dash into delta sigma r dash plus delta sigma E dash, fine. So this is 0, fine. So we will get a relation between the delta sigma r dash and delta sigma A dash, mu dash divided 1 minus mu. So this is the path or the how the sigma r dash and sigma a dash will vary during the unloading. This is governing by this equation. And in the TSS dash clause, the relation is given by delta t by delta is equal to 1 minus 2 mu dash. And in the PQ plot, it's 1 minus 2 mu dash divided by 3 into 1 plus mu dash. Now we have some stress states, some examples of the stress paths. It's going to be very interesting to discuss. We have 4 states. This is the initial isotropic consolidation. Sigma A is called sigma R. We are going to do it in the PQ plot. Fine. We have the initial state P0 and we have given 4 different cases. So initial point where this sigma A is called sigma R, if we like determine the P for it, or P dash is equal to better to write incremental form. So delta P dash is equal to sigma A plus 2i sigma A divided by 3, it will come out to be sigma A, and delta Q dash is equal to sigma A minus sigma R, which is 0. So it will be simply a point on the isotropic line represented by P0. Fine. Now the first case, delta sigma A is equal to delta sigma R. What we have done? We have increased the axial strain and radial strain, stresses, axial strain and radial strain by equal increment. Let's assume there was a confining stress of 30 kPa. We are increasing the axial and radial by another 30 kPa in the both x and y direction. So what will happen in the increment? Delta sigma A is equal to delta sigma R. Fine. So delta P is equal to sigma A plus twice delta sigma A divided by 3. Since both are equal, so delta P dash is equal to delta sigma R or delta sigma A, and delta Q will be 0. Again, if we are incrementing in the same amount, it is not going to deform the sample. So delta Q will be equal to 0 and delta P dash is equal to delta sigma R. So from here to here, we have a increment of delta sigma R. Correct? Fine. Now the second state, we have delta sigma R is equal to 0. There is no change in the radial stresses, and delta sigma A increases. So it means that we are not going to change the whatever be the sigma R, we are keeping it there, and we are increasing the sigma A. How it will look like? So we will first determine the delta P. Delta P is given by sigma A dash, delta sigma A dash plus twice delta sigma R dash divided by 3. Since there is no change in the radial stresses of sigma R, it will go to 0. So we are left with sigma R, delta sigma R dash by 3. And delta Q is equal to delta sigma A minus delta sigma R. This is 0. So delta sigma A is equivalent to delta Q. So now how this point will move from point 1. From here, whether it go to here or here, we will see. Now we will see there is no change in the radial stresses, correct? So it means that this is positive, delta P is positive, and this delta Q is also positive. So whatever the slope, so they are increasing, like both are positive. It means that it should lie in this plane only, first plane only. Fine. And what will the slope? Delta Q by delta P dash equivalent to delta sigma A. This divided by this, we got to be 1 by 3. So it means that it will increase by there's an increase, it will go to the right upwards, and the slope of the line will be 1 by 3. Fine. So Q is 1, and here you can see that is a 3, 1 by 3. Correct. So this will lie in first plane only. Now there is the case C, where delta sigma R is equal to minus times delta sigma A. The radial stresses are actually decreasing, and the amount of decrease is equivalent to the decrease in the or the change in the delta sigma A. So P dash delta P dash is equivalent to delta sigma A dash plus twice delta sigma R dash divided by 3. This is delta sigma A dash minus this delta sigma R is minus times delta sigma A dash. So it will get reduced to minus 1 by 3 delta sigma A dash. and delta q dash is equal to delta sigma a minus delta sigma r dash, which is equal to twice delta sigma a dash. So q, now you tell me that p is decreasing. So if you can see, you can think it is a plus plus, both are plus in this. We don't have a state which is going beyond this. Fine. Here both are negative. Correct. Now it's negative q. Q is negative in this plane and p is positive. Fine. I mean, say like it's like this direction p is increasing, this direction p is decreasing, upward direction p is q is increasing, downward direction q is decreasing, like that only. So now p is decreasing, so p is decreasing. It means that if we are decreasing, it means though it will go this side. So p is decreasing, it means go this side, not horizontally, but it will have a slope. And if we talk about q is increasing, so increasing, and like it will go, it has to go in this direction, and also it has to increase. So it will go something like this with a slope of -6. So you have written here like this. Fine. This will be the this 1 3 represents this stress state. Now we have the another D part. Delta sigma r increases and delta sigma a decreases. So delta sigma r is increasing and delta sigma a is decreasing. So we have to represent this in the stress part. So delta p dash is equal to delta sigma a plus 2i delta sigma r dash divided by 3. So delta sigma a is decreasing. We have represented by minus sign, minus delta sigma a dash plus 2i delta sigma r dash divided by 3. So we will separate it. So it's minus delta sigma a dash divided by 3 plus 2i delta sigma r dash divided by 3. And delta q is equal to minus delta sigma a dash plus delta sigma r dash. Now you can see this is negative, correct? The delta minus delta a will be it's increasing. Fine. So this term will be negative, and this term will be positive because it has a since delta sigma r is increasing and it is increasing 2 folds than this. Fine. So this term will be positive and this term delta q, it will be negative. So what will be the slope of this line? Given by delta sigma a dash divided by 3 plus 2i delta r dash divided by 3 divided by minus delta sigma a plus delta sigma r dash. Now where should it lie? So delta p is increasing, so it should go in this direction, and also delta p is decreasing, so decreasing means this way, this and this, so with a slope of this. So the stress state will be something like it has to go like this, increasing sign, also it should go decreasing in the q direction. So this will be the corresponding line state. Fine. Now we have the another topic to discuss is the stress state for stress path for the sedimentation. Now over the time when for example soil is getting poured, generally it happens over the river beds when there's a alluvial soil is getting deposited. So there is an initial deposit, it will be NC soil because but the soil will be below, it will be having a first time it is experienced that kind of stress, so it will start consolidating. Like next time another deposit will come, it will start to lay over it, and again it will undergo the consolidation. Now due to this process there will be the layering of the soils over it. Now there can be the removal of this overburden. So due to the removal of these layers, the pressure can decrease, the pressure is reduced. And how it will fall? Let's assume OA is the initial state of the soil. Fine. And when it start to the pressure start to decrease, it will decrease from A to B. This sedimentation, for the sedimentation process, the stress path moves from A to B. On further removal, soil would become OC, because if you see, for example, this is the soil. Fine. Initially there is this layer, then another layer came, then another layer came. So this is the maximum stress it has achieved in the past. Fine. Now with this removal of the overburden, let's assume it was 30. Now this layer got over, so now it remaining is 20. So 20 is the stress it is having in present, and 30 is what it has experienced in the past. So it will be in the OC state, and the stress path will further move down to the isotropic line as the as the sedimentation will go over, or the removal or the overburden pressure is getting reduced. This will further reduce to the isotropic level or isotropic line. So this is the stress path for the sedimentation. Now elastic stress paths. What elastic stress path means? It is like when the soil is sheared, elastic stress path can be predicted assuming elastic behavior up to yield point. You have seen that in the stress stream plot. We have discussed this point, yield point, or yield point. So for this state up to this part, how the stress path will look like. And when the soil is sheared, elastic stress path can be predicted assuming elastic behavior until yield point is reached. Or we can see like this. This is the yield point. So we can how the elastic stress path can be predicted for the soils which are sheared up to the yield point. Fine. So we know that the equations for the strain, principal strains in the axial direction, maximum principal strains similarly for the minimum and intermediate, we have the equations like this. Fine. Now for the undrained triaxial compression, so epsilon 1 dash is equal to epsilon a dash, delta sigma a dash is equal to delta sigma 1 dash, and also we have this formulations. Once we will use these formulations, we will obtain the axial and radial strain, and then volumetric strain is given by axial strain plus 2 times radial strain. And for the undrained test, volumetric strain is 0. Fine. And this u dash is not 0 for the undrained test. That is another thing. And this u dash is like it's for this side. For the elastic stress path, u dash is something different. And this for the undrained condition, this u dash is not a 0, but this volumetric strain is 0. So which will reveal that delta sigma a plus 2i delta sigma dash is equal to 0. And if we remember this equation, delta p dash is equal to sigma a plus 2i sigma r divided by 3. So if we multiply 3 times delta p, it will equal to sigma a plus 2i sigma r. So it means that sigma a plus 2i sigma r. So this, or since it is incremental, we can write increment here. So it means that delta p dash is equal to 0. So how the stress path will move? It will be a vertical line. Fine. So the change in p will be 0, and whatever the q will be increasing, or the slope of the line will be infinity. Fine. So this is an important point to note. Now in the TS plot, how it looks like. So delta t is equal to sigma a minus sigma r divided by 2, and delta s is equal to delta sigma a plus delta sigma r by 2. So delta is equal to delta t by delta s. This is going to be this. Then we will use a relation delta sigma a is equal to minus times twice delta sigma r dash. We will get the slope of the line in the TS plot as 3. And we can generally, you see if the soil is in the failure in compression tension, the tensional strength is high as compared to the extension, or compression strength is high as compared to tension, and they are related in the TS plot as TFC, which is the strength in the FC, divided by TFE, strength in the compression extension, given by 3 plus tan alpha dash divided by 3 minus tan alpha dash. So this was all about the week 7, in which we started with the shear strength, a brief overview of the different behaviors observed in the UU, CU and CD. Then the different criteria based on the stress stream plot. That depends upon the user which criteria he want to use, depending upon the soil he has considered. Then the what are the limitations with the triaxial testing, and what are the factors affecting shear strength. And then we checked the we discussed the stress path, which we tell that it's a 2D representation which relates the stress parameters, whether it can be sigma A, sigma R, T and S, or P and Q. Why it is important? It actually helps us to understand how the soil is the failure, or and also it's important to replicate any field condition where like for example there is excavation, or we are building any embankment. So in that situations it becomes important to know how the stress change in the soil, which can be represented by PQ or the stress paths. After that, there are three representations based on the axial sigma A, sigma R, Q and P and T and S. Then how we are plotting this stress paths, why, and also we have discussed in this, the stress path is meaningless unless we define the bounds. If we have the bounds, we can know up to what point we have to lower the soil, and beyond that we can't expect a soil state to be existing. Fine. Then the stress path for the isotropic consolidation in all the three representations. Then stress path for 1D consolidation. After that, for some stress paths, some examples of stress paths based on the variation of sigma and sigma and sigma R. Then the stress path for sedimentation, elastic stress path, how it is varying, and then we discussed the strength in the compression and the extension in the TS plot. Now we will start with the example problems. So before that, we can have a break of 5 minutes. After that we can start. Till that you can just go through the content and let me know if you have any doubt. We can check and discuss before going on before solving the example problems. So we resume now. So question number 1. Two cylindrical specimens A and B of soil were loaded as follows. So we have two soil samples A and B, and they are loaded as follows. How? Both specimens were isotropically loaded by a stress of 200 kPa under drain conditions. Fine. So we can write A and B both have been consolidated at a confining stress of we can write sigma 3, 200 kPa and 200 kPa. Right. After that, subsequently, the radial stress applied on a specimen was held constant, and the axial strain was incrementally increased to 440 kPa under 100 conditions. Okay, it's for specimen A. Subsequently, the radial stress on specimen A was held constant. Right. So for specimen A, what we had done, that radial stress are constant. So delta sigma 3 we don't have is equivalent to 0. We don't have changed radial stress, but what we have done, we have incremented the axial stress to 440 kPa. So sigma A is equivalent to 440 kPa, incremented from that value, from this value to 440, incremented from. After that, the radial stress kept constant, and the axial stress is incrementally increased to 450 kPa under undrained conditions. So from axial stress increased from 200 to 440 in case of specimen A. Now for specimen B, and the conditions are undrained and soil is elastic. So these two things you should remember, these two conditions what we talk about, undrained and elastic. Now what about the soil B or specimen B? The axial stress on B was held constant. So delta sigma A is 0, change in stress is 0, and the radial stress was not increased, or we can see it is decreased to 50 kPa. Radial stress was decreased to 50 kPa. Decreased to 50 kPa. So here sigma R is equivalent to 50 kPa. From here to here it has been decreased. Fine. Correct. Under drained conditions, and we have drained condition here. What we have been asked, plot the TSP, total stress path and effective stress path for each specimen. Calculate the maximum forward pressure in specimen A, and assuming that both the soils are elastic in nature, elastic soils. So when we have been told that these are elastic and these are undrained, so this thing should come in our mind. Elastic stress bar. It will be a elastic stress bar. Correct? Fine. So how we are going to solve this? I will show this step by step. So this is the question. We have been asked to plot the TSP and effective stress plot. Fine. Now the first and foremost thing is it's better to state the things in incremental form. So delta P dash is equal to delta sigma 1 dash plus delta sigma 3 dash divided by 3, and delta Q is equal to sigma 1 dash minus sigma 2 dash. Fine. Now since the conditions are axisymmetric, it's a cylindrical specimen, that's why I wrote this formula, and in the initial part it has been told that they have been both specimens have been isotropically loaded. So at this point, like when we are telling it's isotropically loaded, so delta sigma 1 is equal to delta sigma 3. I mean, if we talk about total stresses, and the conditions are drained, so this will be equal to 0. So delta P dash is equal to delta P, which is equivalent to delta sigma 1. So how much is delta sigma 1? So consolidation has been done at a stress of 200 kPa. It is 200 kPa for both the sides. Fine. Or we can write it simply: P naught is equal to P dash is equal to 200 kPa and Q is equal to 0 because both the stress are 0. So this is the initial condition of the soil for both the soils. Now I will draw a line here. For A soil, A specimen and B specimen. For A specimen, delta sigma 3 is equal to 0. There is no change in the radial stresses, but the change has been done in the axial stress. It has been incremented to 440 from the initial value of 200, because once we are done with the consolidation, we have the all-round stress of 200 kPa. Now this stress has been incremented to 440. So delta sigma 1 will be equal to the difference between these two stresses. Fine. So delta sigma 1 will be equal to 240 kPa. Fine. And delta sigma 3 is equal to 0. For B, it's for specimen A. Now for B, delta U is equal to 0. Fine. So delta sigma 1 is equal to delta sigma 1 dash is equal to 0. There is no change in the axial stress, but there is change in the radial stress from final is 50 and initial is 200. Fine. It's minus 150 kPa. Fine. Now we have the delta sigma 1, delta sigma 3, delta sigma 1, delta sigma 3. Can we find the delta P? Delta P is equal to delta sigma 1 plus 2 times delta sigma 3 divided by 3. So which is equal to delta sigma 1 is 240 plus 2 into 0 divided by 3. So delta P is 80 kPa. Fine. And also delta Q, delta sigma 1 minus delta sigma 3. Delta sigma 1 is 240 kPa and delta sigma 3 is 0. It means that P and Q, delta P is 80 and delta Q is 240. Now similarly for delta P for specimen B, so delta P will be equivalent to delta P dash is equal to delta sigma 1 plus 2 times delta sigma 3 divided by 3. So delta sigma 1 is 0. This is minus 2 into 150 divided by 3 is 300 by 3 minus 100 kPa, and delta Q is delta sigma 1 dash minus delta sigma 3 dash. These are drained, so it's sigma dash, and it doesn't have effect of pore water pressure. Delta Q doesn't have effect of pore water pressure, so it is delta sigma 1 is 0, minus 150 is 150 kP. So this is the like the P and Q values during the once we have done an increment. So what is the current state now? If we write the current state, this is the incremental state during the increment, and this was the initial state. Fine. Now for the current state, can you write P? What is the stress P? P is called P naught plus delta P. What is the initial P? 200, and delta P is 80. So equivalent P is equal to 280 kPa. Correct? Now P dash will be equivalent to P naught plus delta P dash. Now what is delta P dash? Now since the conditions are undrained and the specimen is undrained, so delta P dash will be 0 because the elastic soil. So P naught is 200, it is 0, so P dash will be 200 kPa. Fine. What about Q? What about the Q? So right here. Q is equivalent to Q naught plus delta Q. So it was 0 plus delta Q is equivalent to 240. So it is 240 kP. Fine. Correct. So we have P, we have P dash, and we have Q also. Now for this specimen B, P is equal to P dash given by P naught plus delta P. P naught is 200 plus delta P is minus 100, is equivalent to 100 kPa, and Q is equivalent to Q naught plus delta Q. Q naught is 0 plus delta Q is 150, so it is 150 kPa. Fine. So we have the stress states now. If we talk about the total stress, it is 280, 240. 100 state, we show it by P. P dash is 200 and 240, and here we have Q state given by 100, 150. Fine. So can we plot the total stress and the effective stress and load? It is P dash Q, and let's assume that this is 100, 50, 100, 150, 200, 250, 300, 300, 50, 100, 200. Fine. And similarly 50, 100, 200 and 300. So what is the stress state for the, if we let the initial state is here, it denoted by A, or not A but some another, let's call it O. Fine. So P will be at, if we talk about the total stress path for P, it will be at 280 and 240. So 280 lies somewhere here, and 240 is here. So let's assume this is the point. Yeah. So this is point P, 280 comma 240. The total stress is total stress envelope, it will be TSP. What is the effective stress path? 200, 240. 200, P is 200, it will not change. 240 it will go up to this point. This is the P dash point. 200, 240. This is effective stress path for specimen A. Now for specimen B, it's 100, 150. Fine. It has started from this point O and reached the 100 and 150. 100, 150 is here, represented by Q 100, 150. Fine. So this is the total stress path or effective stress path for the specimen B, because both will be same. Now we have been asked to determine what is the maximum pore water pressure. So the difference between the total stress path and effective stress path will be the pore water, and you can see, for example, delta P is equivalent to delta P dash equal to delta P minus U. Fine. So delta Q is equivalent to delta Q. So there is no change, like the Q will not have any effect of U. The change will be in the P. So whatever be the change in the P, that will reflect the that will give the pore water pressure. So we can write that U is equivalent to delta P minus delta P dash. Fine. So delta P is 280. So U is equivalent to 280 minus 200, which is given by 80 kP. So maximum pore water pressure is 80 kP. Fine. So this is a solution for this. We first identified the initial state, then the increment, during increment what are the P and Q, then what is the current state, then we have plotted on the total stress and on the PQ plot. Now we have another question. If the axial stress on a cylindrical specimen or sample of a soil is decreased and the radial stress is increased by twice the decrease in axial strain, what it's saying is that delta sigma A is decreased. Fine. We represent it by minus delta sigma A, and the radial stress delta sigma R, it has been increased by twice the decrease in axial stress. So it has been increased by twice the decrease in axial stress, so 2 times delta sigma A. Fine. Now we have to determine the slope of the, we have to show that the slope of the line is what? Minus 3. So can we determine the delta P? Delta P dash, so delta sigma A dash plus 2 times delta sigma R dash divided by 2. It is minus delta sigma A dash plus 2 delta sigma A dash divided by 3. So it is minus delta sigma A dash divided by 3. Correct? Okay, I had a mistake here. So it's minus delta sigma A plus 2 into, here it is radial stress, and delta sigma R, we have to replace the delta sigma R is equal to 2 times delta sigma A dash. Fine. 2 times delta sigma A dash divided by 3. So 2 is 4, 4 minus 1 is 3 divided by 3, it will be delta sigma A dash simply. And what will be delta Q? Delta sigma A dash minus delta sigma R dash, which is delta sigma A dash, which is negative, plus is decreased, and minus 2 is delta sigma A dash, as delta sigma R is equal to delta sigma 2 times delta sigma A. So it will come out to be minus 3 times delta sigma A dash. So slope of the line is Q by E dash minus 3 times delta sigma A dash divided by delta sigma A dash is equal to minus 3. So the slope of the line in this case, in the case where the axial stress is decreased and radial stress is increased by twice the decrease in axial stress, we have shown that slope of the line is minus 3. Fine. Now another question is there, question number 3. The initial mean effective stress on a soil is P naught dash and Q is 0. The initial state is given. If the soil is linear, elastic, isotropic material, plot the TSP and ESP for the following axisymmetric undrained loading condition. Please note these lines. Linear, elastic, isotropic material, undrained conditions. Immediately it should reflect that you have to take that delta P dash is equal to 0. What you have to do? You have to we have to plot the TSP and ESP for these two cases. Fine. The first thing that we want to do is we want to write delta P dash equations, which is delta sigma 1 dash plus 2 times delta sigma 3 dash divided by 3, and delta Q is equal to delta sigma 1 minus delta sigma. Fine. And delta P dash is equal to, if we write in the effect in terms of effective stresses, delta P minus delta Q. Fine. Now we know that from the previous modules, delta U is equal to B times delta sigma 3 plus A times delta sigma 1 plus delta sigma 3. Fine. We want to determine this delta U. Fine. So B is equivalent to 1 for a like it is saturated sample, and A is 1 by 3 for elastic isotropic material. Fine. So if we put here, so delta U is equivalent to it is 1, it will be delta sigma 3 plus 1 by 3 delta sigma 1 plus delta sigma 3. So if we rearrange this, it will be here it is delta sigma 1 minus delta sigma 3. Fine. So 3 times delta sigma 3 plus delta sigma 1 minus delta sigma 3 divided by 3. So it will be delta sigma 1 minus 2 plus 2 times delta sigma 3 by 3. So for this case, delta U is equal to delta P. We remember this. So delta P dash will be equal to 0 for the whole case, which represents the elastic stress path. Fine. Now if we take the first condition, delta sigma 3 is equal to 1 by 2 of delta sigma 1. Fine. We will take the first case. So we can write that for any loading applied to this special material during the undrained conditions, the effective stress path will be like this. It is P, it's Q. Effective stress path will be a vertical line, where delta P is equal to 0. Fine. Now for this case, delta P will be equivalent to delta sigma 1 plus 2 times delta sigma 3 is equal to 1 by 2 of delta sigma 1 divided by 3. So delta P is equal to 2 by 3 of delta sigma 1, which is actually a positive term, and delta Q will be equal to delta sigma 1 minus delta sigma 3. That is delta sigma 1 minus 1 by 2 of delta sigma 1, which will give 1 by 2 of delta sigma 1. What is delta Q by delta P? Delta Q by delta P is equal to delta Q is 1 by 2 divided by 2 by 3 to equal to 3 by 2, 0.75. Fine. Now for B part, delta sigma 3 is equal to minus 1 by 2 times delta sigma 1. So delta P is equal to delta sigma 1 plus 2 times minus 1 by 2 of delta sigma 1 by 3. So it will equal to 0. This will cancel. Delta P will be 0, and delta Q will be equal to delta sigma 1 minus 1 by 2 of delta sigma 1, which is equal to 1.5 of delta sigma 1. What will be the slope? Delta Q by delta P, which is infinite. Fine. So how this will go? This is P dash and Q. So the initial point P naught or P dash. Fine. P naught dash. Now for A, both are increasing. P is increasing, Q is increasing, and slope is positive, so it will move to right, upwards like this. So we will represent it by, let's assume this state we represent by A. So this represents the state A. Fine. Now state B is delta P is change and P is 0. And whatever be the derivative is coming, it is acting on the soil with a constant mean stress. Change is not there in the P, so it will go like this. Not as like this. Fine. So this represents B, and also this B is the effective stress part. So this A is the total stress part. Fine, and this B is the effective stress part. Correct. So this was the question that we have to show plot TSP and ESP for the following conditions. So for A, TSP is this and ESP is this. For B, ESP and TSP and ESP will be same. Fine. So this is all for today's session. So I hope you will understand the things, and you will be able to solve the assignment questions without any difficulty now. So if you have any doubt, you can reach us in the forum, and you can also raise a question there, and we will be there to answer your doubts. Fine. So this was all for the week 7. So we are going to meet on next Saturday between like 3 to 5. Till then, goodbye.